So we're in your chemistry chapter 10. We're going to be talking about selective nonmetals and their compounds in this whole chapter. For the next 8 videos, we're going to be talking about certain nonmetals. As you recall, the periodic table, we'll be going over some of the metals and nonmetals on this periodic table. So the one we're going to be focusing on today is hydrogen. You see hydrogen here? You can see hydrogen basically is a non-metal, although at certain states it will act like a metal. Hydrogen atomic mass is 1, atomic number 1. That means one proton. And where it's found, sun and the planets, is actually the most abundant element in the whole universe. So, and the symbol here and the name. So this is what you need to know about the periodic table. So we'll be going on that on each one of these elements. So now let's get going with hydrogen here. So first of all, before we go on to the element of hydrogen, we need to know really what these elements are, how they apply in our lives and affect our aspect of life. So we're going to be talking about descriptive chemistry, which is a survey of the chemicals and processes that are important to our daily lives. We're going to see how hydrogen affects us. We know it's an important element, but really, how would it affect our lives? If we didn't have hydrogen, we wouldn't be able to live. We wouldn't be able to have water, in fact, because water is H2O. Water has hydrogen in it. So these things are how, this is going to tell of our descriptive chemistry, and that's what these next 2 chapters are going to be about, is describing chemistry in how it affects our daily lives. So hydrogen, again, is the simplest element, and it's most abundant in the universe. 70% of the total mass of the universe and 90% of atoms, of our atoms everywhere, have hydrogen in them. So 90%. Hydrogen occurs on Earth primarily in its chemical combined forms as a part of covalent compounds such as water, and constitutes of petroleum. So basically, as we know, because hydrogen can combine covalently with other molecules, it appears in lots of molecules. So hydrogen has 3 different isotopes. Remember, isotopes have a different number of neutrons. Well, 99.989% are protium. And what protium basically is that we have the atomic number and the atomic basically being hydrogen, having that, 1 proton and 1 electron, so that's our basic. But sometimes hydrogen will appear with extra neutron instead of proton. So basically the protium, you think of one, basically 1 proton, and then deuterium you're going to be able to see with a neutron, and then a third isotope is going to have 3-1, which is called tritium, and it's very rare in nature, but it can be produced in nuclear reactors only, so very, very rare. So tritium, we say tritium would be 3. So basically you're going to have 2 neutrons and 1 proton, right? And then two would be 1 and 1. So anyway, as you can know that, just different isotopes and what isotopes are. Well, let's talk about some of the properties of hydrogen. So let's go on to the next. Hopefully I can change this here. Okay, dear. There we go. Okay, there we go. So hydrogen. Hydrogen's melting point is a negative 260 degrees centigrade, and its boiling point is negative 252 centigrades. And it has very weak molecular force. It's called the London force, and we talked about that before. So when you see hydrogen in its natural state, it's going to be very light and a gas. So when you get at low temperatures is where you see the melting and boiling points. It's colorless and odorless. It's tasteless. It's very flammable, so it can ignite very quickly. So let's look at these pictures. You hear one, here's a picture of it igniting in the Hindenburg there. So in fact, it says the tragic burning of the airships Hindenburg in 1937, in which 36 of the 97 passengers and crew lost their life, was due to hydrogen being highly flammable, and led to the exclusive use of non-flammable helium for lighter air. So in the midst of this, of course, hydrogen can ignite very quickly. So it's well suited for balloons and blimps and dirigibles. And so it was used, hydrogen was used in these. Now, mostly they want to use helium, and because of the problems with hydrogen being so flammable. So let's go on to the preparation of hydrogen. So the most common way of preparing hydrogen is with steam reforming. So in steam reforming, methane gas, right here, methane gas reacts with steam as the two gases pass over a bed of nickel. The nickel is kind of used as a catalyst to make it happen. And the temperatures are very high when they do this steam reforming at 600 degrees to 1,000 degrees, and at a pressure of 8 to 50 atm. So they have to have heat and pressure to do this. And so you'll see here with steam, the catalyst, and how in the equation would see, always in these equations, just look here. So here we have the result is a mixture of hydrogen and carbon dioxide right here, and carbon monoxide. So steam reforming has to do with using carbon in the mix. And this methane gas has carbon in it. So we have carbon, methane gas here, and H2O gas, which is really H2O is water, so it would be like water vapor. And then under this, it would turn into basically change components, change it around here into carbon monoxide and 3 hydrogen gases. So now we have made some hydrogen gas. The carbon monoxide is reacted with water to produce more hydrogen then. So the carbon monoxide here. So then it reacts again with water vapor. And now you can see here it turns into carbon dioxide and hydrogen. So this is basically when they ask you how do we make hydrogen, or how do we produce hydrogen, especially in laboratory. You can see how they do it at what temperatures and how they react. We'll see with each one of these. So going on here, and so in the laboratory, they'll do hydrogen they'll use zinc with hydrochloric acid. So here we have zinc and hydrochloric acid here. So very good. Zinc, is reacted with the hydrochloric acid because zinc molecules is solid. Hydrochloric acid here, and then the zinc changes over and combines with the chlorine, which zinc and chlorine combine very readily, and then in the midst we have hydrogen gas. So that's another way, and that's how they usually like to bring forth hydrogen gas in the laboratory. Also, electrolysis. What is electrolysis? Electrolysis is basically putting electric current through. It's electrolysis of water is a method of preparation. Pure hydrogen is in doing this. Electrical current is passed through the water, and it has a small amount of sulfuric acid there. And then the water is decomposed and hydrogen gas comes out. So just think of electrolysis. So we have in the laboratory naturally, and this is how hydrogen is produced. So let's go on here. Here's some pictures here. Here's a picture of the laboratory electrolysis of water here, and how they do that with the cathodes, and they put electric current through the water to get the hydrogen to come out, right? So this is important. The ability of some metals to absorb hydrogen is used in a method of hydrogen purification. The metal palladium is 800 to 900 times the volume of hydrogen, and it's formerly essentially a solution of hydrogen with a crystal sulfur of the metal. So basically, in this thin-walled palladium vessel, the solution of hydrogen, this crystal structure of metal, it becomes this crystal structure as other gases do not dissolve in the palladium. So let's go over that a little bit. Basically, the metal can absorb its volume of hydrogen. It's not going to absorb other type of elements. And this forms a central solution of hydrogen with the crystal structure of the metal. So the impure hydrogen is passed under slight pressure into a thin-walled vessel there. So other gases do not dissolve in it, so that this separates the hydrogen. Just another way with palladium, just think. So they're just telling the way, different ways. Reactions now. Hydrogen forms ionic hydrates containing hydrogen as one ion, hydrogen ion there. Basically with the electron, with the hydrogen electron there, so it's a negative ion with the elements. So hydrogen can combine with groups 1 and 2, except Be, barium, or yeah, okay, let's go on. Be and the molecular hydrates, okay, for example. So here's some examples of it combining. So we have sodium, Na is sodium, and it's combining with hydrogen. And basically, we're actually having, as it combines very easily, you have sodium with 1 and hydrogen with 2. So anyway, you have 2, you see how it's balanced out there? So this is with group 1. So let's look at group 1 of the periodic table so I can show you this. So, so here's hydrogen, and here's group 1 here. So this is going to show how it, all these here, which would be lithium, sodium, potassium, rubidium, calcium, all of these here will, combine with hydrogen in this method. You see how they're combining. So if you had potassium, which is in that group 2, group 1, it would look like this equation. So instead of putting Na sodium, you put potassium, which is K. And then it also now combines very easily with group 16. In group 16 is oxygen. So let's look at group 16. Group 16, as we go over on this side, here's group 16. We have oxygen, sulfur, selenium, and down this aisle here. Mainly, we're going to talk a lot of oxygen. Oxygen and sulfur are very common. Hydrogen combining with this oxygen and sulfur. That's group 16. So the equation would be oxygen 2 with 2 hydrogen 2. See how this goes? And it would turn into basically, you'll see 2 hydrogen, 2 and oxygen, which H2O is water. So you see how that combines very easily. Oxygen, hydrogen forms water, right? And so group 17 is all of group 17 combined very easily with hydrogen. It's one of the groups that are very reactive with hydrogen. And group 17, you'll see. Let me go group 17, clear over on this side. Let's get a little closer maybe so you can see better. Group 17 is all in red here. So all of these groups are very reactive with hydrogen. Fluorine, chlorine, bromine, iodine, all the way down here. So especially these top ones, which we'll go over later. So you can see then the reactions. Basically the reactions of group 17, group 16, and group 1 are very reactive with hydrogen. Okay, so now let's go on to its uses. This is a question. The primary use of hydrogen is the synthesis of ammonia. So that's making ammonia from elements H2 and N2. What's N2? Nitrogen. So nitrogen reacts very easily with hydrogen. And they use this process in making ammonia called the Haber process. How are we going to remember Haber? Well, remember it starts with the H like hydrogen. So Haber process is basically making ammonia. And hydrogen is also used to produce vegetable oils. And these oils are obtained from cottonseed, soybeans, corn, coconuts, and they have many double bonds with hydrogen. Addition of hydrogen to some of these bonds is the presence of a catalyst. So they need a catalyst. So The primary use, of course, again, is making ammonia from the Haber process. And let's go on for a picture of this in the next page. Okay, this is called hydrogenation. Generation, or genation, I should say, is the double or triple bonds, and too much hydrogen results in hard, brittle oils. So this is very, very common in things like, butter, and making it so that it won't be liquid at room temperature. So it's called processing, or hydrogenation, right? So you'll see these in foods especially. So here's a picture of it. So you'll see the double and triple bonds. And you see how basically here we have the carbon here, and you'll have two hydrogen. Well, you have other, basically other units here in the midst. R means that there was another molecule attached there. Well, hydrogen will come in and fill in add the hydrogen to the molecule, so to the substance. So that's how hydrogenation is basically adding hydrogen. Also, liquid hydrogen is an excellent rocket fuel, and it's non-polluting. And the only combustion product that it has from the hydrogen is water. So reaction 10.6. So let's look. Let's see if I can find 10.6. So let's go back. All right, I can't find 10.6 in there, so we'll go back to that later. So anyway, you can be used as a rocket fuel. And also, it can be burned in an oxygen-hydrogen torch at 2,800 degrees centigrade. It can melt quartz or platinum. It's also used for underwater welding. So those are some of the things. It can be used in these practical ways. So the oxygen of deuterium D2O is called heavy water. So basically, this D would mean hydrogen, like H2O, but it's going to have an extra isotope, which is an extra neutron. And so it's a very heavy water. It's used as a coolant and also a moderator in nuclear reactors. So in contrast to H2O, D2 is moderately toxic. If you take it, you can't actually drink it like water. So if it has extra isotopes, it's not a good thing to do. And because tritium is the other isotope, it's radioactive. And so it has these tiny fluorescent coated capsules of gaseous tritium are used to glow in the dark on the needles and stuff. So tritium, that with the extra isotope of hydrogen, is very rare. So so let's go down to this part here. Is pretty interesting, and that's talking about metallic hydrogen. Do you know that hydrogen it's in the column of the metals, right? As I said before, here's the different, as for the metals here, it's in that column, but it's a non-metal. But come to find out, like I said before, in certain circumstances, it can be considered in group 1, it could take the form of an alkali metal. So at very extreme high pressures, though. In 1935, they found that this metal that was strong, shining, it was conductor, and it also was very lightweight, and it remained stable. It was hydrogen. It was the most common metal in the solar system. In fact, Jupiter and Saturn in that picture there are mostly hydrogen, and a lot of this hydrogen is in a hydraulic and hydrogen metal form. It would be the lightest of all metals, 1/10 of a steel bar. So it may be in this, if you read this article here, it says it may be that hydrogen will be a metal of the future, because it'd be 5 times more efficient than rocket, as for in a rocket. Basically, it says here, let's read, in addition to its possibilities as structural material, hydrogen metal could serve as a very compact source of fuel. It is estimated that rocket engine using hydrogen metal as the fuel source would be about 5 times more efficient than the best chemical fueled rockets of today. So hydrogen may be, metallic hydrogen may be a thing of the future. So that's about it for hydrogen. Let's go on to the questions here, and then we'll be done with hydrogen. What is the most important commercial method of preparing hydrogen in the United States? Well, remember the steam reforming from the steam, in the midst of taking out hydrogen out of the water vapor. Steam would be the first, most important. Steam reforming, it's called. And a method of preparing hydrogen chemically in the laboratory would be using zinc, would be a good way, and how they basically, in the process of using zinc, we went back, you can go back in there, and I went over that, in that process of changing the zinc with the hydrogen. So write the balanced equation showing the reactions between hydrogen and potassium fluoride and sulfur. So, so basically, let's go back to that point, because each one of these will be very easy. We'll go back there, but let's list 2 important uses of hydrogen. Well, the synthesis of ammonia. They use hydrogen to produce ammonia. Ammonia is very important. And also the hydrogenation of vegetable oils is adding hydrogen to the vegetable oils to make it so it's not so, the oils are not so liquid, and they will you can actually use it commercially, and it's easier in the solid state. And a lot of people do not like this because it's actually, adding to making a certain product or that we eat a little bit different by adding, processing it. They call it processed food with hydrogenation. Okay, and there's 2 other kind of uses. Also, fuel and rockets. So we went over rocket fuel, making of ammonia. Those are some of the things you can put down for that. So let's go back to this potassium fluoride and sulfur. Remember that? Let's go back to that and see if I can show you how easy this is. You'd basically go back to the equation where they put together with sodium. Let's see. Okay, missed it here. Oh, here it is. So in the midst of here, we have, instead of putting, we have sodium and hydrogen making, as we go through potassium, we can take potassium, which is K, and potassium, of course, is in the same group as sodium. K right there is potassium. So we take K and we just put K in here, and instead of where the Na is, and put K, and that's the way we do with K. The next is fluorine, and fluorine is a group 16 with oxygen, or well, fluorine is, in group 17. It's a halogen, so it's in 17. We call that group of high reactors here. We'll go over them later here. This group here, high reactors, fluorine and chlorine and everything. So, and they react very readily with hydrogen. And so we have chlorine. So instead of putting chlorine here, we would just put in F, which is fluorine. It acts the same way. So it'd be fluorine here, and basically the CLs, you put the Fs in. And the other one is sulfur, and sulfur is in group 16, which is oxygen. The oxygen is right here. Here's sulfur, right? And so it would act the same way as oxygen. So we just put in S2 right here, and 2 hydrogens, making hydrogen sulfide. And you just put, and where the O is, you put S in. So you probably might have to do this on a test or something, but it'll be very easy. So that's all we're going to do for hydrogen with the questions. So next we're going to go over oxygen. I'm going to go quicker over as we go over these, as we go over each one.